Intro to Deep Q Learning, Simple Inverted Pendulum Demo. I have a video on Q Learning. With Q Learning, we'll run into trouble with problems that have large state spaces. Discretizing the state space can be very difficult or impossible. Therefore, it has been proposed to replace the Q table with a neural network. This neural network will take as input the states of the system. Then it predicts actions based on those inputs. In this way, the algorithm can efficiently handle complex state spaces through learning features and state representations. First, we need to create a class for the agent. Import the necessary libraries. This is our agent class. The constructor declares important parameters, including the input and output sizes of the neural network, and mathematical constants. An array called the replay buffer stores experiences, initialized to DQ and neural networks. I will use TensorFlow to create the neural networks. For those wondering what the result of the build underscored function is, look here. The input equals the number of states provided by the model. The network has two hidden layers, each with 32 nodes. The output is the number of possible actions to be executed. The model is fully connected. This function is for saving experiences, including state, action, reward, etc. This is the function for creating input based on the epsilon greedy strategy. We will split the batch size both to reduce the resource burden and to optimize for finding local minima during backpropagation. This part is for training the model. We will use one neural network to generate an action for the current state, and another neural network to predict for the next state. Update the Q value according to the formula and use it as a label. When training the network, note that when terminated equals true. Only assign the reward because at this point the agent has stopped operating. So there is no next action. Now we'll move to the entry point of the project. We also import the necessary libraries. This train function is used to train the model. We will check and update the weights from the main neural network to the target neural network every 10 episodes. Predict the action. Use the action to interact with the environment to get the state. Save these elements into the replay buffer. If the replay buffer reaches a certain size, proceed with training. Gradually decrease epsilon until reaching epsilon underscore min. Save the model in H5 format. For inference, just load the model and use it. This is the newly trained model in the video. Its accuracy is still low. This is a model trained over 100 episodes with 500 units. As you can see, it balances very well.